Hello.
Yeah, you're audible. I think you can start.
Right. Hi guys. Good morning. So yeah, my name is Himanshu, and I'll be accompanied Girish and Kailash today for teaching you guys some linear algebra. So yeah, I guess we can start then.
Hi,
Right.
people. This is Kailash.
Yeah. Okay. Girish, next slide. Okay. So getting started with linear algebra. Hmm. So to give you some context, let me tell you about like the history of linear algebra. So right, like when we think back at 1600s, when René Descartes, like he was, the pioneer in developing the Cartesian system, right? What he did was he was in a prison cell when he discovered when he invented the Cartesian system, and well, as you can see, like he was bored. Well, not really, but yeah. So what do we use the Cartesian system really for? We use it for plotting graphs. We sometimes use it for like just keeping track of stuff. You plot something along the x-axis, y-axis, something along the x-axis to see how the change occurs. So I mean, this was a system that led to linear algebra basically. So firstly, I would like to say that we can form linear equations with Cartesian systems. So Cartesian systems really have like variables as their axis, like x and y. So if you take a two-dimensional Cartesian system, it has x and y variable. So if we apply some constraints to variables, then we form linear equations. So yeah, we have like a Cartesian system for real plane as well as for imaginary plane. So we have the complex numbers developing, and we have the complex plane as well. So we can apply linear algebra both to real and complex numbers. Then yeah, that's like right. Vector spaces. I mean, it's sort of a really ambiguous term at this point, but if you want to understand what vector spaces really are, which will be covered later on, we need to know what vectors really are. I'm sure that many of you are familiar with what vectors really are, but let's have a small recap. So let's consider a Euclidean space. Now, I like to think of Euclidean space as your imagination. If you close your eyes and if you see whatever space that you see is sort of a Euclidean space. Well, the a formal definition of a Euclidean space would be like anywhere, like a given space where Euclidean geometry, all the laws and properties of Euclidean geometry are satisfied. Right. So, two-dimensional plane, or a three-dimensional space would be a Euclidean space. Now, if I apply coordinate systems to these, for example, Cartesian coordinate, so I will get a Cartesian space for this. So from Euclidean space, I get a Cartesian space. So now a vector, in a sense, would be sort of an arrow or a line segment in a Euclidean space. So I think I can be sure of what the magnitude really is. I can measure the length and I can get the magnitude. But what about the direction? I don't really know what the direction is because I can look at my imagination can be in any direction, right? At the vector. So I don't really know what the direction is. So only when I apply a coordinate system to the Euclidean space, I'll get the direction of the vector. So if I apply a coordinate system to such as the Cartesian system, then I will get a vector, a well-defined vector. So yeah, next slide. Girish. Yeah. So a textbook definition of a vector would be a line segment with magnitude as well as direction. Okay. So we have defined what a vector really is. Now let's consider a two-dimensional Cartesian system, coordinate system. So in this we have two variables, x and y. We know the variable will be plotted against this direction, which is usually considered the y direction, and the x will be considered this way. So you have x and y plane, axes. That's what we call them, axes, right? So now we can represent any point in this space in terms of x and y, where x denotes the weight in the x direction, weight of a point in the x direction. That is like in x direction, how much do you have to move to get the point? Similarly, in the y coordinate will be how much you have to move in the y direction to get to the point. So x comma y, as you can see in the next slide, you can change the slide. As you can see, if I move x in this figure, I've moved like 2 units to get to the x value of the of the point. So that will be the x point, as well as for no, you can go to the yeah, as well as for y, it is somewhere between 0 and 2 basically. So somewhere between there, if I move that much, I'll get the y. Yeah, I'll get to that point in the y direction. So you can see x comma y can be represented as this in the graph. But there is another representation of this point, which will be in the next slide. And it is x cap plus y cap, where x cap is nothing but the direction of the x axis, and y cap is the direction of the y axis. So you can imagine like x axis, which direction it goes to. So how much weight does the x direction have? Like in this case, it is x, and then for y, it will be y again. So yeah. So this is general representation of a vector. It's usually like x cap plus y cap. Sometimes you can also denote it as x I cap plus y j cap. But yeah, it means the same. So yeah, you can go to the next slide. Okay. So a conventional way of representing vectors is as a column vector. This is called a column vector because we are representing the elements of a vector as a column, and we just include them in a bracket. So I mean, yeah, we can differentiate between. Okay, so this is a vector, right? In this bracket, I will keep the elements of the vector. So x and y here are the vectors. X will have the top part will have the x cap direction, and the bottom one will be the y cap direction. If it was a three-dimensional vector, we'll also have another element in the same column, which will be z. So it will be x, y, z, right? But what is the magnitude of the vector? Now, you really ask, like, what is it the magnitude of? It depends upon what the origin really is. If you take the Cartesian system, the origin is 0, 0, where the value of x is 0 and value of y is 0. So we measure the distance between 0, 0 and the given point x, y. So you can guess the magnitude, that is the distance between origin and this point, would be how much? It will be root x squared plus y squared. So in the next slide, I will show you how to generalize this thing. So if you want to generalize something, we could use norm. Okay, so norm is something that uses dot product. Now, a dot product of of two vectors is given as follows. So if we have two vectors, v1 comma v2 and w1 comma w2 as v vector and w vector, then the dot product of v vector and w vector is v1 w1 plus v2 w2. And again, some properties of dot product. A dot product is commutative. That is, you could write w dot v or v dot w. It will give us the same result. I'm pretty sure it's basic stuff. So I'm pretty sure you're familiar with it. So yeah, that is the dot product. And the norm is nothing but the square root of the dot product of a vector with itself. So it sort of gives you v1 v vector dot v vector, which is nothing but v1 dot v1 times v1 plus v2 times v2, which is v1 square plus v2 square. So norm is nothing but square root of v1 square plus v2 square, which gives us the magnitude of the vector. That is the distance between the origin and the vector. So this is the norm and this is the magnitude that you have. And if you want to find the direction, then you can actually find the direction using by looking at the graph. You can use trigonometry, and given that you have the magnitude and you will have the x and the y values given to you, right? It is x cap plus y cap. So if you want to find the direction, tan theta will be equal to y by x, right? Because it's a straight line, it will be a triangle, and you can find y by x, which will be equal to tan theta. So you can find the direction as well. You can get the theta. So this is how you define a vector in a Cartesian space, which is two-dimensional. You can further go to three-dimensional and so on. But yeah, I mean, that's something that you could try on your own. Yeah, next slide. Girish. Okay. So now that we've talked of vectors, we can come to the linear algebra part. So we talk about linear combination of vectors. So what really is linear combination of vectors? Well, to be like very vague, I would say linear combination of vectors. Let's say v1, v2, v3, and so on till vm. I consider this as a set of vectors, set of m vectors. They may be unique, they may not be unique, we don't know. But these are some set of vectors, and a linear combination of vectors is a constant multiplied by a given vector, and there we take the summation of these vectors. So that is a linear combination of vectors. So let's say a1, a2, a3, so on till am are some constants. Now here you would see something interesting. They belong to f. Now what really is f? To be really okay, I'll give a small description of what f is. F is nothing but field. It's called field in mathematics. So field is something in which you can so field is a set of numbers in which you can take two numbers from this set, and you can perform addition, subtraction, multiplication, or division, and the output of this binary operation will belong to that same set. For example, if I take real numbers, if I take 1 and 2, if I add 1 and 2, I'll get 3, which does belong to the real numbers. If I take the subtraction, it'll give me -1, so it belongs to the real numbers. Again, multiplication and division, they belong to the real numbers as well. So yeah, you get the point. So that is the definition of field. In fact, another important thing to note while considering fields, while considering a set to be a field, is that fields they have to commute. Like when you take the binary operations, they must commute, right? So if just because 2 by 1 is, so for example, if you take natural numbers, 2 by 1 will give me 2. But 1 by 2 will give me 1 by 2, right? Half, 0.5, which is not a natural number. So natural number is indeed not a field as such. As a field, you need to be able to satisfy all the binary operations. So that is a basic description of what field really is. So now that we know what field is, we can say like A1, A2, and so on are they are constants that belong to the field. And when A1, V1 plus A2, V2 plus so on till am vn, that is the linear combination of vectors. So that may result in a vector or a plane or anything, we don't know. So that is just a linear combination of vectors. It's just an expression of that we would like to analyze. Okay. Now, if you want to talk about span, okay, so span is it's all the linear combinations of vector v. So we can take a number of combinations like with different constants a1, a2, a3, and so on, and that will give us the span of a now of vector v. Uh, so yeah, we will discuss more on span. If you have any doubts, you can like put it on the chat or the YouTube chat, and we'll be addressing that as well. Yeah. So that was the span. Any doubts in span? It's just a linear all the linear combinations of V, all the possible linear combinations you can find for V. It can be infinite, yeah. It can be infinite. It can be finite as well. We'll come to the examples, yeah. So that is span. You have finite dimensional span, finite dimensional vector spaces where the span of V is just V. Yeah. Okay, next slide. Linear independence. Okay. So now that you have a set of vectors V, capital V, I want to know if these vectors are really dependent on each other. Can one vector affect the other? Can sort of one vector dependent on another set of vectors in the same set? So like what I really mean is, if I give you a textbook definition, then a set of vectors V is considered to be linearly independent if for a given equation a1 v1 plus a2 v2 plus so on till am vm is equal to 0. That is, the summation of them is equal to 0. Then a1 is equal to a2 is equal to so on is equal to am, and all these constants have to be equal to 0. That is the condition for linear independence. What it really means is that the only constant that sort of connects a relation between these vectors is 0. Okay, so I think you will understand much better with an example. So you can move to the next slide. Right. If you want to consider a vector space, a vector set. So we have vectors 2, 5, and 4, 10. 2, 5 here means 2x cap plus 5y cap, and we have the other vector which is 4x cap plus 10y cap. So these are two column vectors. Now, I would like to see if they are linearly independent or not. So is there something that you observe here? I think you do, right? The second vector is actually, like the elements of the second vectors are actually doubled. So they are the double of the first, the elements of the first vector. So you can see like, yeah, exactly. It's linearly dependent, correct. Because the second vector can be represented as the first vector. So if you move to the next slide, you will see, yeah, you can move to the next slide. No, next slide. Yeah. So you can see that the second vector can be represented as 2 into 2 by 2 into 2 x cap plus 2 into 5 y cap. You take the 2 outside the vector because it's a constant. You can take it outside the vector. So it's 2 into 2 x cap plus 5 y cap, which is 2. So if you take 2 comma 5 as v and 4 comma 10 as w, then we get, you can move to the next slide. We get w is equal to 2v. What it really means is that the same vector, the same vector set. I can't change the vector set. It's given to me. It's like something that it's an information that's given to me. But what I can say about this vector set is that I can represent this vector set by just using one, one constant, or one single vector, which is 2 comma 5, right? I don't really need the 4 comma 10 because I know it's given as a vector set, but for proving a linear dependency, I can say if I multiply with a constant, some other vector by a constant, I can get some other vector. That is, I can get v or w and so on. So that is linear dependency of a vector. You can see if a set is linearly dependent or not. So yeah, another example you would see in the next slide. So this was like using a scalar constant. We are multiplying a scalar constant to a vector to get a vector that already exists in a vector set. Now, if you move to the next slide, you can go to the next slide. You will see three vectors in the vector set. Now, I don't really see, like, it's 2, 5, 3, 6, and 5, 11. Can anyone in the chat put if they're linearly dependent or not? You can take your time, like a minute or so. I'm sorry. Yeah, it is dependent. And yeah, sure. I'm pretty sure like the reason is also quite clear. So I can say I can add the first two vectors, the elements of the first two vectors. And if I observe, I will get the element of the third vector. For example, if the x cap component 2 and 3, if I add them, I'll get 5. And if I add the y cap component 5 and 6, I'll get 11. Right? So if you move to the next slide, yeah, as you can see, it is we can see that if I add two vectors, so if I add the components of two vectors separately, it just means that I'm adding the two vectors like as a whole, right? And this addition of the two vectors is giving me the third vector in the vector set. What does this mean? So when I try to take the linear combination of any two, like these three vectors, for example, A into the 2, 5 plus B into 3, 6 plus C into 5, 11, I don't really need that C into 5, 11. Like I can write C into 5, 11 as C into 2, 5 plus C into 3, 6. You can write this down on a note and you can, observe. So it's C into 2, 5 plus C into 3, 6. And this I can, I can take 2, 5 as common. So it will be A plus C into 2, 5 plus B plus C into 3, 6, right? And yeah, A plus C is another constant which belongs to the field. It can be real number or a real field or a complex field. So A plus C can be replaced as K1 and B plus C can be replaced as K2. So I can represent the linear combination as K1 2, 5 plus K2 3, 6. And I don't really need 5, 11 as a vector to represent the linear combination. So I conclude that I can conclude something with this. Now we come to the more general definition of what linear dependence really is or linear independence really is. So a set can be considered linearly dependent if one or more vectors of the set can be represented by an additive or a multiplicative combination of other vectors in the set. So it's like a more mathematical definition of linear dependence. So yeah, I think I've made it clear with two examples what linear dependence what it looks like or linear independence really looks like. So yeah, next slide. If there is any doubt, you can let us know. Okay. Any doubts? Any doubts in the video, in the YouTube thing? Okay. Basis. So what really is basis now? So if I consider a vector set V, okay, it has some vectors and the list of the vectors in V that are linearly independent. So for example, the previous vector set that I took, 2, 5, 3, 6 and okay, we have a doubt. What is a multiplicative combination of two vectors? Okay, of two vectors, I would not say like two vectors. I'm sorry. If I consider like the first example that I took, say like the 2 into whatever the first example was, 2 into 2 by 5, 2, 5. That gave me 410, right? So that is one of the multiplicative combination of one vector, right? I multiply a scalar with a vector to get the other vector. I could also have this. I could say, for example, there are three vectors in a set, and let's say 2 into first, like v1. Let's say the vectors are v1, v2, v3. So 2 into v1 plus 3 into v2. So it's like a multiplicative and an additive combination, right? So you have like two vectors in the which comprise the additive part, and scalars which are like independently multiplied to the two vectors. So that's what I meant, right? Okay. So that was linear independence. When we come to basis, rather, so when we have a set of vectors V, and like in the previous example, we had three sets, right? Which were 2, 5, 3, 6, and 5, 11. So in that, the linearly, so if you see, like the linearly independent part of that vector set V, yeah. So a list of vectors in V that are linearly independent, and they span V. So that is, they form like the linear combination of V. So if I take the basis of the previous vector set, it would be it would be the first two vectors alone, because I need only those two vectors for defining the linear combination, all the linear combinations regarding that vector space, regarding the vector set, right? So the basis for the vector set V would be the first two vectors that are 2, 5 and 3, 6, right? I don't really need 5, 11. So that won't be counted in the basis of the vector set. So that is the basis for the vector set. So it's basically the part of the vector set which is linearly independent and it spans V. So we can form like different all the combinations of linear combinations of vectors with the given two vectors, right? Or how many other vectors are given in a vector set. For example, if I take this, so this is actually called as the identity or basis, because like you see, like each and every vector here, given here over here is independent of each other. So it's an like linearly independent, this given set. And the span, we can represent the span as well, right? So if I try to give out the span, it will be a into the first vector 1, 0, 0, so on till 0. And the second one will be into 0, 1, 0, and so on till 0, and so on. So in the end, what the resultant combination would look like is A, B, C, so on till wherever it goes, right? So that is the it's an identity basis or a standard basis. So this is an example of what a basis looks like. So is there any doubt in basis? The basis is basically like from a vector set, you take the linearly independent vectors, like you take them separately, and they are the basis of the set because they can span V. We can form, like we need they're like the fundamentals for forming the linear combination. Others, like they're like just some linear combination of the given vectors that we have taken separately, right? Like we have taken it separately. Like if we use some additive or multiplicative, right? The span is just telling us any vector which belongs to vector A can be represented by the linear combination of the base. Yeah, exactly. Yeah. So is there any doubt in span? Okay, cool. Yeah, next slide. Yeah, matrix. So matrix. Well, I would define like there is a textbook definition of matrix, of course, in front of you. So like a matrix is a two-dimensional array of elements. Okay. It can be thought of. So what I like to define matrix as. So as an author, if I had to define matrix in my mathematics textbook, I would call it a vector of vectors, or rather a row vector of a column vectors. As you can see, I could represent each and every column, I could take each and every column as a column vector, right? And as a column vector. And I could take every single vector as an element of a row vector. I mean, it's sort of an abstract idea, but yeah, it's better. It makes you like sort of visualize what a matrix really looks like. I mean, yeah, it is a two-dimensional array of elements, but when you think of it like for example, the vector set that I considered earlier, I could think of that as a vector as well, as a matrix as well, right? So it's like 2, 5, 3, 6, 5, 11. That could also form a matrix. It looks like one, so I could say that is one matrix as well. It's two by three matrix where I have two rows and three columns. So 2 by 3 matrix. Similarly, here we have m rows and n columns. So it's m cross n matrix or m by n matrix. So matrix, yeah, it is true. It is a two-dimensional array of elements, but we can also think of it as a vector of vectors. So yeah, next slide. Girish. Right. So if I consider a three by three matrix where we have three elements in the row, three rows and three columns, it will have totally 9 elements. It's obvious, right? So the general structure looks something like this. And we'll call it square matrix because m is equal to n. So you have the same number of rows and columns. So that sort of forms like a square, right? So it's called a square matrix where the number of rows is equal to number of columns. Yeah. So there are different types of matrices. Like I talked about the column matrix, which is also called a vector matrix. We have the row matrix, and then we have zero or null matrix, which is just all the elements of the matrix are just zero. And then diagonal matrix, where all the elements except the diagonal elements. So diagonal elements, I mean, is the one where if you go to the previous slide once, you can go to the previous slide once. So here we have A11, A22, A33. So these are nothing but the diagonal elements, right? So these elements are the ones which are non-zero, or they can be zero, yeah. But like these are like, when you consider diagonal matrix, the elements which are like not the non-diagonal elements, they have to be zero in the case of diagonal matrix. So that is the diagonal matrix. A scalar matrix is a type of diagonal matrix actually, where all the elements in the diagonal are same. For here they have given A, right? So all the elements are A in the diagonal matrix. So that is a scalar matrix. And unit matrix, furthermore, the unit matrix is a type of scalar matrix where all the diagonal elements are 1. So that's a unit matrix. We represent the unit matrix or identity matrix as I. So it's actually a very important, like a useful matrix to remember. So keep a note of this matrix. We'll be using this a lot. And then we have the upper triangular matrix, where all the elements above the diagonal, including the diagonal, are non-zero, and the elements below the diagonal are 0, right? So you can see here. So these three are 0, whereas all the matrices above, all the elements above the diagonal, including the diagonal, are non-zero. Similarly, we have the lower triangular matrix where all the elements above the diagonal are 0, and the below the diagonal, including the diagonal, are non-zero. So that is the lower triangular matrix. So yeah, these are basically the types of matrices. It's like some convention that we use. They're just names. Yeah, next slide. Transpose. Okay, so transpose is actually pretty important to note here because if you consider the matrix as I told you, three by three matrix given. If I take the transpose of it, I'll get another matrix which looks something like this. So it's just I'm flipping the matrix like 90 degrees. It's not 180 degrees, it's 90 degrees. I'm flipping it. So A21 will now be A12. That is, the element which was in A21 will be shifted to the place of A12. And the element which was in A12 will be shifted to A21. So you're just interchanging the positions of the elements, which are yeah, you're just interchanging the position of the elements. Or else you can think of it like this: when you want to take the transpose, you consider the diagonal elements, right? So you sort of consider them as a mirror, like the plane of a mirror. And if you flip this, if you flip this, you will get the transfer of it. Okay, not really a mirror. You just consider it as like a line. And if you rotate this line by 180 degrees, you'll get the transpose of the matrix. So because you're shifting the elements as such, right? And if you shift, you won't really the diagonals won't really change in a transpose, as you can see, because there is nowhere that they can go. There's no place where they can shift really. So a transpose is basically this. Yeah, you can go to the next slide. Any doubt in transpose? Yeah. Yeah, another like this is it really doesn't come under types of matrices, but inverse of a matrix is actually the property of a matrix itself. So inverse of a matrix is like okay, so if you have a real number, let's say 2, what is the inverse of 2? The inverse of 2 is 1 by 2, right? So it's 0.5. So what inverse of a matrix really mean, inverse of a number really means is that if you multiply a number with its the inverse of the number, it will give us 1. Similarly, in matrices, the equivalent of this is nothing but if you multiply a matrix with its inverse, you will get the identity matrix, which I talked of earlier. 1, 1, 1. Yeah. So you'll get the identity matrix. So yeah, that is the inverse. And in order to if a matrix is considered to be invertible, it has to have a determinant which is non-zero. Now, what is the determinant? Well, we'll come to what the determinant of a matrix really is in the further on topics. As of now, it is a bit premature to cover it up. So we're just discussing of the introduction and the matrices. So I don't think that that's relevant right now. But consider it like for a given matrix, it's like okay. For example, if you take a triangle, right, in a coordinate system, so you could fill up those the coordinates of the triangle in a matrix, right? You can fill it up. So x, y, x1, y1, x2, y2, x3, y3, where x1, y1, and so on are just the coordinates of the triangle. And then the third element, you just keep 1, 1, 1, right? So a determinant, I would define it as a property of a matrix which relates to its area, like relates to the area of that triangle. So for a 3 by 3 matrix, it will relate to its area. Well, yeah, it does sound a bit confusing as of now, but I was just giving a small description of what determinant physical meaning is. But if you see purely mathematically, then determinant is sort of an operation that we perform on a matrix, which gives us like something like a magnitude of it. So we'll come to it. We'll come to it soon. But as of now, just know that determinant of matrix should not be 0 if it has to be invertible. Yeah. You can go to the next slide. Okay, so abstract vector spaces will be taken by Kailash. And I hope really that you guys don't have any doubts. If you do, you can just put that in the chat box. Feel free to put that and we'll be covering it up for you. Bye, you guys.
So, yeah, hi people.
One second. Give me 1 second. Before we start, I'll just share today's attendance session. After that, we can proceed. I'll just put the link in all the chats. Okay, I've put it in the team's chat. We'll just wait for a couple of minutes for people to fill this form. After that, we'll proceed. Kailash, you can meanwhile get ready by starting to present.
Yeah, sure. Okay. Fine. Okay. So I think that should have given enough time for you people to fill in the attendance, I guess. If anyone is still filling the attendance, like please do it fast. I'll maybe wait for 30 more seconds or something. Okay, fine. So I'll start. So now, so firstly, I hope you're having a great session till now. And yeah, please, if you have any comments or something on the session, like do write it in the YouTube live chat or the chat box. So now we are going to talk about abstract vector spaces. So till now we've been talking about vector spaces in a particular format. We had a particular kind of image for it, and like we've always thought of it, thought of a vector as some arrow from one point to another. Now that is probably a very good way to think about vectors, but I mean, not like arrows are not the only kind of vectors, you know. there are other kinds of vectors too. So yeah, what we're going to do for the next like 20 minutes or so is sit back, relax, and think like a mathematician. Basically, when vectors was being invented, and mathematicians wanted like to describe a lot of phenomenon, because after all, vectors is a tool, and it has some properties, and you apply the properties to get things. So we are trying to expand our horizons basically to like properly understand the, I mean, the realm of application of these properties, as in what and all things we can apply these properties and get simplifications and stuff. So to start with, let's look at a few examples. Okay, so the first example is a set of all solutions to a homogeneous equation of vector space. So what is a homogeneous equation? So you know linear equations, right? I am assuming you know those. So okay, let's take two linear equations. So a homogeneous equation is something that doesn't have a constant. The degree of every term is 1, basically. And 1 could be x or y. Now, an example would be something like 2x plus 3y equals 0 and 4x plus 5y equals 0. So 0, 0 is obviously a solution, but there are also other solutions, right? Even in the example I said, I mean, 2x plus 3y and 4x plus 5y, you can solve and you'll probably get something x equals something y, and you'll get some solutions for that. So those solutions like x comma y comma z, they are not free, as in you cannot just put any number and make it equal to 0. You get like a particular set of maybe 2 tuples or 3 tuples. So the question is, are those a vector space? For example, if I have only maybe say 10 solutions or something to the homogeneous equation, or those 10 solutions a vector space, as in do they obey some properties that I can group by to make them a vector space? Fine. So the answer turns out to be yes. We'll look at the reason why a bit later, but let's just look at whether the things we talk about are vector spaces or not, to like have a bit of intuition. Okay. So it's a set of all vectors having natural numbers mod 17 as components of vector space. So again, you can like represent these as n tuples. For example, these are kind of one-dimensional arrows. For example, 1, then you have an arrow of magnitude 2 pointing along the x-axis as 2. You have an arrow of magnitude 3 pointing along the x-axis as 3, and so on. But you only have like 16 arrows, right? Because it's mod 17, and you can only have 0, 1, 2, 3, dot, 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 up to 16. So, I mean, sorry, 17 arrows totally. Now, is this collection of 17 arrows alone a vector space? Do they obey the same abstract properties as a general vector space? The answer turns out to be yes. So you can, for example, you can like add arrows. I mean, I'll go into the specifics later, but if you think about it, you can do addition mod 17, and you can like scale arrows. You can do everything that you can do in a vector space. Okay, now this is an interesting example. So for those of you into machine learning, there is this technique called one-hot encoding. So I'll explain what that means. So one-hot encoding is a way to like store data for a classification problem. So let's take an example. For example, let's say Himanshu likes option A, pizza, option B, burger, option C, I mean, dosa or something, South Indian dish, and option D, some puff or something. So one way to store data in a, like Excel sheet or something is to like create one column. For example, like, I mean, the person or the serial number and the thing itself, like dosa, vada, I mean, pizza, burger, for example. And the other example, so if you have those drop downs, right, multiple choice, you have only 4 options. So what you can do is you can represent 4 tuples. So these are like binary numbers. So it's either zeros or ones, and you have 4 elements in the list. Okay, so each list has 4 elements, and those are zeros or ones. If the element is a 0, so okay, and we'll have a predefined convention. So first thing is for burger, second thing is for pizza, third thing is for dosa, and fourth thing is for veg puff or something. So if it is a 0, then it means Himanshu does not like that particular thing. If it is a 1, that means Himanshu likes that particular thing. Now, we are not storing the thing as text. We are storing it as zeros or ones. And we like all our data sets. Like if I were to put a poll, it's stored in this format basically. Like 0, 0, 0, 0 means Himanshu does not like anything, and 0, 0, 1, 1 for example means Himanshu likes dosas and vegetables for example. So yeah, that is a way to store these things. And these 4 tuples I'm talking about, these also form a vector space. So they have like 4 elements, and you can define an addition, you can define like scaling, for example. And like if you look at the previous example, these are natural numbers mod 17. In a way, these n tuples are natural numbers mod 2. So yeah, these also form a vector space. Okay, now we come to a more interesting and like more abstract mathematical kind of example. Is the set of all functions a vector space? And it turns out the answer is yes. So how in the world is someone going to like imagine a function as a vector space, right? Like I mean, a function takes something as an input, something as an output, and where is the arrow, the pointedness? I mean, for me, when it came to know of this just like blew my mind. I mean, the same properties that you could like apply for a function, sorry, a vector space, you could also apply for a function. So yeah, but coming to think about it, what is a function? Okay, so let's talk about 2-dimensional functions for more intuition. So a function is basically something that has an input and an output, right? And so if I were to take let me take a very simple example. Let me take the function f of x equals 2x, right? So I'll take maybe one input. So if I put an input of 4, then I get an output of 8. Any real number can be an input. Now, if you think about it, it's like a little bit abstract, but let me try to model the function. Like, let me make an Excel sheet or something and try to model the function, okay? So the way I'm going to do this is, I'm going to like pass an input, get an output, and then store it in like various rows. So if I take the function f of x equals 2x, so let me pass the input like x equals 1, I get 2, let me pass 2, 4. What if I pass 1.5? I get 3, pi, 2 pi. So I get like, so if you think about it, in the Excel sheet, I have an infinite number of rows for the function. And the LHS will basically carry all the x values and the RHS will carry all the y values, right? So now, in a way, this is kind of an infinite dimensional vector. So the way we're going to think about this is, if I have a vector in like say 2 dimensions or something. So okay, so before that, let me go to the x dimension, for example. Let me take a vector in 2 dimensions. So that's an x coordinate, that's a y coordinate, right? Now these x and y are things that we just give a name to. But we could also have given these things as like a coordinate and b coordinate. We could have named them however we wanted to. So let me call the names as like say 1 coordinate and 2 coordinate. Now the value for the 1 coordinate, the magnitude along that will basically be the value of the function at x equals 1. So yeah, to recap, I'm constructing a vector of infinitely many orthogonal components. It's like a infinite dimensional vector. And the way I'm doing it is I'm labeling each of the coordinate axes as real numbers. So if a coordinate axis corresponds to, say, it has the name 1, then the magnitude of the vector along that, like the component of vector along the 1 axis will be the value of the function at x equals 1. If you think about it, even this kind of forms a vector. This is like a very complicated vector. It has infinitely many input points, infinitely many output points, but still it is a vector. It is a vector space. So yeah, this is a vector space in kind of a way, but the way I explained it is kind of hard to visualize. You can't really visualize infinite dimensions. I mean, trust me, I can't even visualize like 4 dimensions. Leave alone 4, I can't visualize like 3 dimensions fully. So that is another way of like explaining this. And these 4 examples are how like the theory of vectors even came into play. So okay, let's go on to the next one. So the set of all polynomials. Set of all polynomials, a polynomial is a function, and so it kind of makes sense. And also the way you visualize this is you say one, you label the axis as 1, x, x squared, x cube, and so on. So the coefficient of 1 would basically be the component of the vector along 1. The coefficient of x would be the component of the vector along the x direction, and so on. So yes, polynomials are a vector space. What about the functions that are not zero? Okay, so the answer turns out to be no, and that is very interesting. So we'll come to this later, but this will like basically determine a fundamental property of yeah. Oh, fine, okay. So like okay, imagine a three-dimensional vector. So this is like x, this is y, this is z. Now, if you think about it, the x coordinate itself is a convention. Like I'm just naming it as x. An equivalent name could be say, I mean, apple coordinate or banana coordinate or something. Or I could name it with a number like 1, 2, 3 or something. So let's say f of 1 is like say 2 or something. Then okay, let me just take three input points for the function. So f of 1, f of 2, f of 3, and everything maps to 1. Okay. So in the along the 1 coordinate for this function in this space, the space has 1, 2, 3. F of 1 is say 2. Then like there'll be a vector, right? There'll be a three-dimensional vector. Its component along the 1 coordinate will have a like length of 2. Similarly, its component along the 2 coordinate, which is the y coordinate, in this example, will have a thing of f of 2. And its component along the z coordinate will have a length of f of 3. I'm labeling the z coordinate as a 3 coordinate. Like there is an equivalence, I mean. So if I have a function, like consider all the functions with 3 input points. So f of 1 is like say 2, 1, f of 2 is 2, f of 3 is 3 or something. That is the vector 2, 2, 3. There are 3 input points. It's a 3-dimensional vector. And each vector represents a function. Like let's say I have the vector 100, 2, 5. It represents the function f of 1 equals 100, f of 2 equals 2, f of 3 equals 5. Right. So each vector represents a function and each function corresponds to a vector. So the set of all functions corresponds to a vector space. Is that clear? Wait, who? Okay, fine. So moving on. Yeah, so the functions that are differentiable also turns out to be a vector space. So I don't expect or like you to understand this like straightforward, but I mean like at the moment, but just keep this in mind. And as we go on a little bit further, I want you to like look back at these examples and just work out if they satisfy everything. Like that is a nice exercise. So yeah, we've talked about a lot of things like from one hot encoding to I mean some random modulo 17 came to picture, then even more random functions came. So these are like a lot of things, diverse things. I mean, there are much more examples for this, but yeah, what is common between all of these and say the arrow, right? We can visualize only up to a certain extent, and like for a mathematician, just visualizing it is not enough. We need some like abstract, like concrete things, basically. Things could be abstract, but they should be concrete. So yeah, we need to like come up with a set of properties that relates all these. So yeah, now we'll go on to talk about properties. So the way we are going to do this is vector spaces are also called as linear spaces, and we're talking about linear algebra, as you probably have heard of. Now, we'll just assume that the mathematician who found out linear functions, like linear spaces, took the motivation of homogeneous linear functions. Like probably he was looking at functions of the form y equals mx, and he was like, okay, maybe this could be represented as a vector or something, and maybe he found like vector spaces was actually invented that way. I'm not very sure about the history behind it, but I think I can convince you enough to show that someone could actually come up with the entire idea of vector spaces through this basic idea. So yeah, y equals mx, we are assuming it to be a linear space, and we're going to look at the properties between these vectors and all the abstract things we talked about. So y equals mx. So basically, what is that? You take an input, and the output is a multiple of an input. So let's say y equals 2x. I mean, okay, or a different example. Let's say y equals 25x. So the input x equals 1, y equals 25, x equals 2, y equals 50. So you're scaling the like output as a function of the input. Right? You're scaling the input to produce the output. Now, note that in all the examples I said, like a common thing is addition. So basically, you can add two functions, for example. You can add two vectors. If you have something mod 17, you can like add the components mod 17. Addition is a common thing. So that could be a property of a vector space, and that is indeed a property of the vector space, as we shall like choose. And addition. So like let's take a step back. What is addition? So you take two elements, you perform an operation on them, and you get an output, right? So this addition operation, it has to have some nice properties, right? So commutativity, right? Commutativity is obviously a property. You take, for example, 1 plus 2, that is equal to 2 plus 1. This is like very obvious. So commutativity is a property. Associativity, 1 into 2 plus 3, 1 plus 2 plus 3, you put 2 plus 3 in a bracket is 1 plus 2 plus 3. So yeah, and let's say addition of vectors. V1 plus V2 is the same as V2 plus V1. And V1 plus V2 in the bracket plus V3 is the same as V1 plus V2 plus V3. So the elements of the vector field itself have an operation addition defined on them. And this addition is commutative and associative. Let's look at this in the perspective of like linear functions. So for a little bit more intuition. So you have two linear functions. So y equals m1x, y equals m2x. So you look at y1 and y2 as the vectors themselves, and x as the coordinate. Like for example, so you look at y1 and y2 as the objects themselves, and x as the input, and the x comma y as the vector. Okay. So like let's look at it in two dimensions. So let's take the example y equals 23x and look at it. So y equals 23x in the Cartesian plane, that function will be a line, right? As you all know, y equals mx is a straight line. So y equals m, like m1 is the magnitude of the vector, right? And you don't have a direction because you only have one axis, which is the x-axis. As in, so yeah, we are talking about two viewpoints here. And one viewpoint is a Cartesian viewpoint. So you have a straight line and you're adding one more straight line and you get a third straight line. And the other viewpoint is, in order to represent the straight line, I'm considering only one axis, that is the slope axis. And you're adding two slopes to get a third slope, right? So let's look at how these slope vectors, let me call them slope vectors, work together. So if I add two straight lines having two slopes, so to represent the straight line vector, I will use y1 and y2. So what is y1 plus y2 in the Cartesian plane? You're adding two straight lines to get a third straight line, right? y3. Now, what is the slope of y3 here? Now, if you look at the slope thing, slope picture, I have m1 as a vector, m2 as a vector, and I want to add these two. So that is m1 plus m2. Now, regardless of whether I add y2 plus y1 or y1 plus y2 in the Cartesian plane, I'll get the same straight line. So addition is commutative, the addition of slopes or straight lines passing through the origin. That is commutative, right? So can you like visualize this as a vector, a one-dimensional vector, the slope thing itself? So in the case of linear, in the case of linear functions, the slope is a component of a vector and addition of slope is different. Now, let's go to the next thing, which is the no example. So let's look at the no example. The no example was functions that don't pass through the origin. Now, what is origin? Like origin is just a point, right? So, but the origin is like quite a special point. So the origin is 0, 0, 0 in like how much ever dimensions you want. Like every element is 0. Now, in normal like arithmetic, 0 is called the additive identity, right? Now, if you have an element, say 1 or something, you can, in integers, I'm considering integers. So 0 is the additive identity, and I have 1 on one side of it. And also in integers, I have -1. So 1 plus -1 is 0. So now I have an inverse. So I call -1 as the inverse of 1. So inverse is of an element in a given field. For field, Himanshu should have explained what a field is. We'll go through that later also. Is basically defined as over an operation. So inverse of an element over an operation on this field is an element on this field such that when you operate this element on the first element, you get 0. So the inverse element of 1 under addition in the field of integers is -1 because 1 plus -1 gives 0. Now we will like as you go through a lot of examples and you want to like apply properties, you will understand that this 0 feature is like extremely essential for linearity's sake. So you have a line like in the linear function example, you do have a straight line having slope equals 0, right? Y equals 0x. So if I add the line y equals 0x, the thing to let's say y equals 2x or something, I get the same line back like in the Cartesian plane, right? Y equals 0x is the x-axis, y equals 2x is some line like this, and if I add those two, I get y equals 2x back. So a 0 element exists in the case of linear functions, and we shall also consider this as a property for a vector space in general. So till now, is there any doubt as such? Is it fine? If you have any doubts, like just put it in the chat. Fine, okay. Moving on ahead. Okay, so third operation is so now we've covered addition. What is repeated addition, multiplication? So in the case of like one-dimensional things, you can like multiply them easily. But what is multiplication in the case of vectors? So you would have already thought like talked about dot product, cross product. There's like a lot of multiplication like things involved. But we're not going that far, okay? We are going a little bit closer to home ground. So we are multiplying by we are talking about scaling as multiplication. So think about the first time you were introduced to multiplication. You have 2 mangoes, you multiply that by 4. So you have 4 baskets of 2 mangoes. You're scaling it in a way. This is the kind of multiplication we are concerned about at the moment. So what are we doing? We are taking mangoes and we're multiplying that by 2. Now what is this 2? Obviously 2 is not a mango, right? So like what exactly is 2? So 2 is an element. So but think of, you can easily say these kind of terms. But what kind of element? I mean, 2 is a natural number, for example. But the context of mangoes, natural numbers does not really make sense. I mean, a mango would not know what a natural number is. So there's a little bit more like natural underlying factor order to all this. And that is fields. So a field is a set of elements that a vector can be multiplied by. So if I have mangoes and I want to multiply mangoes, the number which I multiply the mangoes by all the possible numbers. For example, I cannot multiply a mango by pi, but I can multiply a mango by 2 in a very idealistic kind of world. Like if I have 2 mangoes times 2 is 4 mangoes or something. So all these elements are called a member of a field. Now I'm not saying these elements have to be natural numbers, whole numbers or something. If you can define a multiply by in a certain sense on a vector with this number, then this number will be a part of the field. Okay. Now let's take an example in the case of linear functions. So in the case of linear functions, the real number is the field. I mean, and in the case of because you can like multiply the slope by any real number, right? So you can define a multiplication of a slope to give another vector. I mean, another slope within the uh, giving another real slope itself. So yeah, real numbers is a field. R power 3 is a field. So the set of all three tuples is a field. And what is natural numbers is a field. So yeah, a field is like kind of abstract, and what we look at is the properties of a field. So you have to elements of a field can be added to and multiplied with each other. So if you take the example of real numbers, two real numbers can be added to multiplied by each other. There is an additive identity. There's a multiplicative identity for a field. And if you take modulo 17 also, that is quite interesting actually. So you can add two numbers modulo 17 to get a third number that is modulo 17. For example, if I add like 8 and 12, say, I get 20. 20 is 3 modulo 17. And I can also multiply two numbers modulo 17. For example, 2 into 3 is 6. 6 modulo 17. And say 10 into 2 is 20. 20 is 3 modulo 17. So that is multiplication. And the modulo 17, 17 is a prime. So this prime is quite important actually. You'll get to know that like in a bit of higher math. So in like modular arithmetic, if you have a prime number, then the I think there's a property that says the multiplicative inverse of every number exists. For example, in base 17, the multiplicative inverse of 2 is like 9, and the multiplicative inverse of 9 is 2, because 2 into 9 is 18. 18 is 1 more 17, and 1 I call as the multiplicative identity. So yeah, natural numbers mod 17 is a field and things like that. And one important property of the field is closure. So if you do operations on a field, you should get a member within the field itself. Like I just cannot do an operation, say, like, I mean, maybe I cannot define an element infinity in the real field, for example, unless I define every operation that belongs to the field. So I don't have any examples right now to show otherwise, but the closure is quite important. And yeah, the multiplication, as we've talked about, addition is commutative and associative. Similarly, multiplication must also be commutative and associative, and an inverse must exist. Like we talked about in modulo 17 case, the inverse of every element actually exists. So that is also very important. Now we've talked about addition multiplication. So we can keep adding properties like this, but when do we know that we are actually done adding enough properties? I want you to think about this for like 30 seconds or so, because I mean I want you to think of various other properties we can add, because like in the case of 3D vectors, you can define a dot product, a cross product, or something. So how many properties are you supposed to add, and can you define a dot product, say, for functions? Like, so yeah, going on. Okay, I want to tell something, point out something interesting. You can actually define the dot product for functions, and that will involve a little bit of higher maths, but that will kind of be equivalent to the integration of two functions. Okay, so this entire vector space thing that we're doing for like finite dimensional things, that will kind of turn into an integration like operation, the dot product, for an infinite dimensional case. So dot product is valid. But what about cross product? I mean, what does it even mean to do the cross product of two functions? Do you think, like, I would honestly like to know your opinion. Do you think a cross product can exist in like any vector space? Maybe I'll put a poll. Adri, can you put a poll? Okay, so yeah, I look at the results, but I'm like interested. Like, do you people think cross product is like a operation in every vector space there is? I'm telling you that dot product is always there. Okay, interesting. So, no. Okay. Anyone has any reason for that, or is this just like I don't know what a cross product is, so I think it's no. If you have a reason, type it out in the chat box. Like, okay, there is 2 yes entries. Nice. Maybe I should make myself a little bit more clear. So, what do I mean by cross product existing? So, I want to define a general operation for any vector that if I take to the Cartesian plane, like 3-dimensional plane, that general operation should give me the cross product operation. I want to generalize the cross product for any vector space. Correct. Yeah, cross product is also a vector. Yeah, for cross product we need 2 vectors. You can like take 2 vectors themselves and operate on them. But yeah. Okay, so the thing is, till now mathematicians haven't found a good enough cross product generalization for higher dimensions that can even go to infinite dimensional things. In a way, dot product is kind of special because there are a lot of properties associated to dot product. For example, a vector dotted with itself gives the magnitude of the vector the whole square and something. But for some reason, which is deeper, we haven't been able to like define a cross product for an abstract vector space. For finite dimensional vector spaces, we can indeed define a cross product, I think. But if you think about it, like a cross product, one of the basic things is if you have 2 vectors, the cross product is perpendicular to that vector. Now, how will you define a cross product in 2 dimensions, in a 2-dimensional space? You don't have a perpendicular to 2 vectors always. And how will you define a cross product even worse in a 4-dimensional space? You don't have you have infinitely many vectors perpendicular to 2 given vectors, right? In a 4D space. So because of these difficulties, suitable cross product hasn't been like defined. But let me tell you, a lot of people have tried to do this, and a lot of work has been done, but till now we haven't got a satisfactory answer. Maybe in the future we could like define a good operation or something. But yeah. Okay. So what about adding a constant? So I'm talking like the slide is in the perspective of the linear function thing. So if I have a linear function f equal y equals 2x or something, is the addition of plus 3, like y equals 2x plus 3. Is that operation valid? I mean, so in this vector space, I think it's pretty obvious. We've talked about this before also. We're talking about homogeneous linear functions. I would like to remind you that. And at 0, these functions need to give the value 0. And if I add a constant, at 0, these don't give the value 0 anymore. Like y equals 2x plus 3, these like it gives the value 3 or something at 0. So we are like going outside the possible realm of vectors by adding a constant. But so yeah, this is not a valid operation on linear things, but I can now generalize the linear function to a function plus an element of degree 0. So that is possible. So yeah, that is why spaces are like fields are quite important. We need to define the set of vectors which we are talking about to define the operation perfectly. For example, we just can't define adding constant for like let's say the set of all homogeneous linear equations. But we can do that if we talk about polynomials. So one way to do this is you consider x as one direction, one as the other direction, and if I add a constant, I'm adding it in a perpendicular direction. In a way that kind of makes sense, no? Because I mean, think about it. Fundamentally, the direction x and the direction 1, you cannot get x no matter how many ones you add, no matter what you multiply it by. They are fundamentally different, right? So in a way, you can imagine them to be orthogonal. So yeah, if I consider the set of vectors to include every kind of function possible, that is polynomial and of maximum degree 1, then the addition of constant is a operation. Now, these operations are specific to like special vector spaces, and I wanted to point that out too. That was the purpose of this. Like, I mean, various vector spaces have various special operations on them, depending on the geometry, depending on the like topology, for example, and stuff like that. But we are talking about like in abstract vector spaces, we are talking about simple things which work for everything. So yeah, I covered this. So orthogonal components, you can never get an x coordinate thing simply by adding how much of constants you want. So in a way that is orthogonal. Now we talked about addition and multiplication. So one more important thing we need to keep in mind is the relation between these operations. So we talked about addition separately, we talked about multiplication separately. But we kind of need a relation between these two. And that relation is distributivity. Now, why do we need a relation? Because in the real world, I'll be doing multiple operations of addition and multiplication and stuff like that. And if I have, like let's say, A times B plus C or something, I also want to maybe simplify it a little bit, or I want to view it from a different way. This is like a fundamental property of addition and multiplication. So it kind of needs to be there because I mean we are used to it, but distributivity is not a given thing. It is something we take. Every real number field obeys distributivity and stuff like that. So this is kind of very important. And like let's say we have v1 plus v2 and we do c times v1 plus v2. Now this is not saying it's simply, it is not like saying it's like, I mean, c times 1 plus 2 or something. It's v1 plus v2. What if we take c times f1 plus f2, right? So this distributivity operation is kind of important for these kind of things because we are finding two ways to get the same vector. And yeah, that is the fundamental idea of distributivity. Now, yeah, I would like to end this with a like very simple question. So we defined an abstract vector space and we defined two operations, addition and multiplication. Now we'll come across enough examples to convince ourselves that commutativity, distributivity, associativity is enough, and like inverse, existence of inverse. But how do we know no other property is true? Like, I don't know, I can't imagine anything right now because I'm completely attuned to these four properties, but I don't know, like some random property between addition and multiplication could be true. I mean, one thing is that like mathematicians haven't found anything else or defined anything else in the real world. I mean, in kind of a way, we model maths after real world, right? So yeah. And the truth is we don't. Like, the thing is basically, mathematicians are very clever. They research a topic like for a long time. They think about a lot of basic fundamental properties. And once they get enough, they just stop. So what we did, we basically defined a set of objects, vectors. two operations. So v1 plus v2, c times v1, and we also have a field which I haven't written, but we also have that. Now we don't want to, like, let's say addition of a constant, for example. Not every vector space has that. We don't want to put too many properties, too many operations, but we want to put as many as possible, but which is still abstract, which is still general. I can apply it to a lot of things. So that is the fundamental notion of mathematicians, and like for some higher reason which even I don't know, maybe mathematicians have just stopped with this vector space. We've just taken two operations, some relation between these two, and some properties. And it turns out we can actually do the analysis of a large number of structures, functions even, with these vectors, with these vector analogies. So yeah, minimalism, right? So that's what we mathematicians like aim for. We want to punch like we want to pack the largest punch, the smallest packet. So yeah, hope you had fun, and I'll pass on to Girish for like the next part, elementary row operations. Girish. Oh, by the way, if you have any doubt, you can like ask. Now's the time. Okay, fine. Yeah, Girish, go on.
Kailash, can you stop?
Yeah. Yeah, done.
We have discussed a lot about vectors. Let's come to matrices. Like, I'm Girish. I want to introduce something about matrices, like some spaces which are related to matrices, like row space, column space. First, we'll start with elementary row operations. Elementary row operations are just multiplication of a non-zero constant with a row. We are applying these operations on a matrix, any given matrix. The application of these 1 minute. The application of these elementary operations is to obtain a very well-defined form of a given matrix, a row echelon form. It is obtained from given matrix by applying elementary row operations. This form should be in such a way that, as shown on the screen, 0 rows means the rows which containing all zeros must be at the last of the matrix. Column numbers of pivots, like pivot is a first non-zero element in the given matrix. For example, here in this matrix, in the second row, the pivot is -3. Like that, the first non-zero element in a given row is called pivot of that row. And the column in which a pivot is present is called pivotal column. 0 rows must be at the last of the matrix, and column numbers of pivots must be increasing, and every pivot must be 1. Like, I will show an example. First, we want to find the row echelon form of this matrix. What we are exactly doing is, first we'll make every first element of every row as 0, as shown here. By applying these operations, we will make every element of first row 0, and sometimes while making the first element 0, we may get second element also 0. Like if we have 1 2 2 4, if we subtract 2 times, we may get both as zeros. By applying these operations, we can get these matrix. Like, first we will make every row first element 0, then we will try to make second element 0. What exactly we want to do is, if like non-zero element in every row is called as pivot, we want the column number of pivot to be increasing. Means there are starting some zeros. like let us call the number of zeros is x, the column number of pivot will be x plus 1. This should be increasing. Means as we go from top to bottom, we want number of zeros in a row to be increasing. For number of zeros in a row to increase, we will apply these operations, and first we will make every element, first element of every row 0 except the first row. And by applying similar operations, we can make second element 0 like that. First we will make the every element of first element in the every row 0 except the first row, and we will obtain this matrix like 1 2 3 4 5 6 3 2 5. Consider this matrix. We want to find row echelon form of this matrix. The row echelon form is like in every row there must be some leading zeros, and the number of leading zeros should be increasing from top to bottom, because first non-zero element is called pivot and its column number should increase. Means first non-zero element should shift to right as we move from top to bottom in every row. So number of zeros must increase. What we have to do is, as number of zeros should increase, first we will make every element of the first element of the every row is 0 except the first element, except the first row, sorry. Like that we can make as shown, we can make that way. And now what we are doing exactly is, we will make second elements of the last two rows 0. Like first row we will keep all the elements non-zero, second row we will make 1 0, third row we will make 2 zeros. Like that we will increase number of zeros this way. Now if for suppose accidentally two rows have same number of zeros, we can make them like here 0 0 12 and 0 0 minus 6 in the matrix shown here. The number of zeros in these two rows are same. Now if the number of zeros in the two rows are same, the second row can be made more number of zeros simply by doing a row operation. Like R4 is doubled 0 0 minus 12. This first element, this first non-zero element in this row can be made 0 just by doubling this row and adding with this row. Like that we can increase number of zeros in every column, and after increasing number of zeros, this is the only task we have to do. We should get a form in such a way that number of zeros are increasing from first row to last row, except for the 0 rows. Sometimes we may get 3 0 rows. Like in all the 3 rows, every element is 0. In that case, we can leave those rows at last, as shown here. 0 rows must be at last of the matrix, and in non-zero rows only the pivot is there. So in non-zero rows only pivot is there. So column number of pivot should increase up to the last non-zero row. In 0 rows there will not be a pivot. So the second rule is no need to check the second rule in the 0 rows. Up to last non-zero row, the column number of pivots should increase. And after having a form as shown in here, 1 2 3 0 minus 3 minus 6 0 0 12 triple 0. After getting a form this way, we can make every pivot 1 just by dividing it with first number. Like here we have 1 2 3 0 minus 3 0 minus 3 minus 6 0, this matrix. We want to make every pivot 1, just we can divide with the first element so that it becomes 1. So making every pivot 1 and making placing 0 rows at the last is not that problem. But what is the basic problem to convert a matrix into row echelon form is, we have to get a form in which number of zeros at the start of every row should increase from top to bottom. How would we attain this is the problem. Like here first we will consider the matrix. As I told before, we will make every first element of the row is 0, and sometimes we may get second element also 0. First we should, the basic problem as I told, it is to increase the number of zeros from top to bottom should increase. We should get a form like this. How we will attain that is the problem. If we are able to do that, we are completed to attain the row echelon form. Here first we consider the matrix 1 2 3 4 5 6, this matrix, and we made first element of every row is 0 except the first row. Like there are 4 rows. First row we will leave as it is, and second row we will get 0 1 0, third row 2 zeros, fourth row all zeros. We may not able to get this way. Sometimes we may get first row first row no zeros, second row 1 0, third row all zeros, fourth row all zeros. We may get that way also. But what we are trying to do is increase the number of zeros. For increasing number of zeros, what we will do is first there is no zero in any of the rows. So first we will introduce first zero in the every row, like as I shown here. R2 minus 4 R2 changes as R2 minus 4 R1. Second row will be changed as second row minus 4 times the first row. 4 minus 4 0, 5 minus 8 minus 3, 6 minus 12 minus 6. We will get 0 at the first column of this second row, sorry. Like this way we can get 0 at the first row. Now after making every first element of every row except the first row as 0, we want to make third row. First row has no zeros, second row has 1 0. So number of zeros has increased from first row to second row. Now number of zeros should increase from second row to third row also in row echelon form. So what we have to do is we have to get 2 zeros in third row. For getting 2 zeros in third row, what we are exactly doing is, to avoid fractions, I multiplied this third row with 3. Directly we can do R3 minus 4 by 3 times R2. Like what exactly we are trying to do is we have to make second element of the third row as 0, because number of zeros should increase. As there is 1 0 in second row, we have to get at least 2 zeros in third row for number of zeros to be increasing and to attain row echelon form. Here is the form we have with 1 0. Now what we have done is we made second element of third row as 0, and if 2 elements of the third row are 0, as number of zeros should increase, the second element of the fourth row also must be 0. So we made second element of fourth row 0 together with the third row. Like we considered R3 minus 4 R2. We got second element of the third row as 0. Similarly, R3 plus 2 R2 we are doing by R4 plus 2 R2. By doing that operation, we get second element also 0. This way we got 2 zeros. Now we have to make 3. For number of zeros should increase from third row to fourth row also. Like number of zeros should increase from every row to next row. For there are 2 zeros in third row, 2 zeros in fourth row. So number of zeros should increase. So we made 3 zeros in last row. This way we made our row echelon form. Now after obtaining the systematic form of the matrix in which number of zeros are increasing from row to row, it is easier to obtain row echelon form. What exactly we have to do is, as number of zeros are increasing, the second rule is satisfied. So 0 rows must be at last of the matrix. This will also be satisfied. What exactly we have to do is every pivot must be 1. So we will divide as shown in this matrix from here to here, 1 2 3 0 minus 3 0 minus 6, from that matrix to last matrix. What exactly we are doing is every row is divided with its first element, so that first element will be equal to 1. First non-zero element will be. After getting row echelon form, we have another form of the matrix which is row reduced echelon form. All the rules are same except that all elements in pivotal column except pivot must be 0. What exactly we have in this matrix? This is row echelon form of the matrix we have considered previously. Now what exactly for row reduced echelon form, what exactly should happen is, this is a pivot, this is a pivot, this one is a pivot, this one is pivot, and this one also a pivot. Now all elements in a pivotal column except except the pivot should, here this is a pivotal column, because this is pivot, this is a first non-zero row in this matrix, and this is also a pivot, and this is also a pivot. Sorry. So here the first element in the every row is pivot. So this, as we already discussed, the pivotal column is the column which contains the pivot. As this is pivot, the first column will be pivotal column, and second column also a pivotal column as it contains this pivot, and third column also will be a pivotal column because this contains this pivot. So what exactly we want to do in row reduced echelon form is, we have to make these non-pivotal elements in a pivotal column. Like in this second column is a pivotal column. In that one is pivot. Now 2 is a non-pivot. We have to make that the element at 2 also 0. In row echelon form, the elements in a pivot need not be 0. But in row reduced echelon form, one minute, I was gone with settings.
Hello, is there any issue?
How to stop annotation, bro? Like I was stuck with that. I'm unable to change the slide.
In Canva, is it?
No, in Teams.
You stop sharing and share again. Select one of the options and click submit. In the forms, I mean close the forms or something.
Once close that form, bro, like I'm unable.
Sorry, that Arthur has. Wait, you're only sharing, right? No, just like select one of the options, bro. Select some random option.
I'm unable to select that option also.
Oh, right. 1 second, I've tried it. Okay, I'm not exactly sure. Like, can you rejoin Teams? I think that will be easier.
1 minute. I'm unable to select any option. Like
one second. I'll remove you from Teams and add you again. See if that works. Others, please wait for a couple of minutes. There is some technical difficulty. We'll sort it out soon.
No, okay, bro.
Yeah, okay. Now try sharing again, see if it works.
1 minute, I'll share screen. Now what exactly we have to do with row reduced echelon form is all elements in the pivotal column except pivot is 0. So here in pivotal column, here every column is pivotal column because one in every row is pivot. So all the columns 1, 2, 3 are pivotal columns. So we have to make this 2 in the first row, which is in a pivotal column but not a pivot. what we have to do is all elements in pivotal column except pivot are 0. So consider the previous example. We have considered the same example. We have obtained row echelon form by doing row operations. What we are doing now is non-pivotal elements in a pivotal column. Like here, two in the first row, 3 in the first row, and 2 in the second row are now non-pivotal elements, but are in the pivotal column. We have to make those also 0. How can we make them 0? Uh, like here we have, for making 2 0, for making the term at 2 to be 0, we can remove 2 times the second row from the first row. Like if we want to make a non-pivotal element in a pivotal column to be 0, we have to remove the row in which this non-pivotal element is there. Here 2 is the non-pivotal element. We have to make the 2 to be 0. Now we have to remove the row containing this non-pivotal element from the row which is containing the pivotal element corresponding to this non-pivotal element. Like here 2 is the non-pivotal element. For making it 0, we will remove this. We will subtract the second row, 2 times the second row from the first row. As you have seen here, the element at the place of 2 became 0. This way we can make it, every non-pivotal element can be made 0. Non-pivotal elements in pivotal column only can be made 0 this way, because we can remove that row, we can subtract the pivotal row, the row containing the pivot, from the row containing the non-pivot which we want to make 0. Now elementary matrices is just there are 3 elementary matrices which corresponding to every elementary operation. What exactly elementary matrices are doing is converting that row operation into a matrix multiplication. Here Eij is the matrix obtained by, these are the definitions. Like Eij is the matrix obtained by interchanging I and jth rows of the given unit, like the unit matrix which is in the order of the given matrix. Like we will see an example. This is a proof. First we will consider a random matrix equation A B equal to C for any 3 arbitrary matrices A, B, C. Now A1 is the matrix obtained by exchanging ijth rows of A. Now consider A1 into B equal to C1 will be the Now how C1 will look like? It will look like the ijth rows of C are interchanged, because when we first we will consider this AB into AB equal to C, we will multiply ith row of A with every column of, multiply with this ith row of A with every column of B to get the ith row elements of the C. Like if we want to get Cij, I row jth column element of the ith row jth column element of the C, what we are doing is we will multiply ith row and ith row of A with jth column of B. Now if we interchange ij rows in A, what exactly will happen is we will multiply this jth row with the columns of B to get the this jth row elements of C. Now if we interchange the rows, what exactly will happen is the ij rows of the matrix C will also get interchanged. Is everything okay? Like any doubts in this part? If we interchange rows of A, the rows in the product also will change with the fixed matrix. Like if we interchange rows of A B equal to C, A1 B equal to C1, A1 is obtained by interchanging rows of A. So C1 will be C1 also will be the one which is obtained from interchanging rows of C. Is this thing clear or any doubts? Now we will substitute A equal to I in above equations. IB equal to B, like multiplying I with any matrix will not change that matrix. Like I is like multiplicative identity for the matrices. I into B will be equal to B. Now if we interchange ij rows of A, like A1 will be the matrix obtained by interchanging ij rows in A. Here A equal to I. So we
One second, I think you're muted.
from when? Like
From like just now only. Like
okay.
yeah.
Now by definition, what A will be? A1 will be Eij, because A we have took A equal to I, so A1 will be the matrix obtained from I by interchanging I and j rows. As from our definition, this will be Eij, like just it's just a notation. So C will be equal to B. Now C1 will be what? C1 will be C1 will be the matrix obtained by exchanging Ij rows of C, ij rows of C, which is B itself here, because I into B is equal to B, so C is equal to B here. So C1 will be the matrix which is obtained by interchanging ij rows of B. So Eij into B is equal to matrix with ij rows exchanged in B. So exchanging two rows in matrix, in given matrix B, is equivalent to pre-multiplying it with the given the standard elementary matrices Eij. This way, similarly multiplying ith row with a non-zero constant is equivalent to pre-multiplying the given matrix. Pre-multiplying means the multiplication is done before, like Eij into B, not B into Eij. Pre-multiply means the matrix is multiplied in front, like Eij into B, not B into Eij. Similarly, all row operations are converted into matrix multiplications. Exchanging two rows of a matrix is multiplying the given matrix with Eij. Multiplying a row of a given matrix with a non-zero constant is multiplying with it with E alpha I. By similar proofs, we can do that, like subtracting C times jth row from ith row, like third row operation we have now here. We can subtract a scalar number of times of a row from another row. Ri changes as Ri minus alpha Rj. This can be done just by multiplying with E minus C Ij, which is the row operation is applied on I and then multiplied with B. Like I into B is equal to B. Now if we apply that, the operation we want to apply on B, we will not apply directly on B. We will apply it on I and multiply that matrix with B. If we want to interchange rows, we will interchange the rows of I and multiply that matrix with B. So that matrix will be Eij. Multiplying Eij with B will interchange the rows of B. Now, null space is a vector space of matrix which is interlinked with matrix. Like it is a vector space and related to matrix. It is for a matrix, like null space of given matrix, like that. Null space of the given matrix is set of all vectors which are satisfying Ax bar equal to 0 bar. Multiplying that vector with given matrix will give the 0 vector. I mean here not 0 vector here, denoted by n of A. Properties of the null space are that matrix, if a matrix is of order m cross n, for this multiplication Ax bar is equal to 0 bar. Ax bar to be defined, that x bar should be in the order n cross 1. So all the vectors in null space are n cross 1, and every vector in null space is orthogonal to a row, because if we are multiplying with a matrix, if we are multiplying a matrix with a vector, what we are doing is this x bar is a column vector. It is of order n cross 1, so it is a column vector. We are multiplying the given matrix with a column vector. So for this multiplication, what exactly we will do is we will multiply every row of the given matrix with only one column vector in the x bar. Like x bar is a column vector, so there is only one column. We will multiply every row of A with a column of x with only column of the x, and we will get ax bar product. Zero vector ax bar equal to 0, so a product of every row with a given x bar is 0, means the x bar must be orthogonal to every row, because that is exactly dot product na. A into x bar means rows of a into x bar we will get zeros in the right side. So the vector x bar is orthogonal to every row in the given matrix. This is another point. Applying row operations will not change null space. By applying row operations, the null space of the matrix will not change. We will see why. Like here we already told every vector in null space is orthogonal to every row, so it is orthogonal to linear combinations of rows. Let us consider a matrix x bar in null space which is orthogonal to R1 and R2. R1 and R2 are rows of the matrix. Consider any linear combination of R1 and R2, like R1 plus R2. If that vector in null space x is orthogonal to R1 and R2, it will be orthogonal to x bar. X bar will be orthogonal to any linear combination like A R1 bar plus B R2 bar, like dot product of A and B 0, A and C 0. Then A dot lambda A plus mu B will A dot lambda B plus mu C will be 0. So A will be perpendicular to any linear combination of the rows, any two rows in the given matrix. So by applying row operations, what exactly we are doing is, if we interchange two rows, there is nothing, like we will change the matrix, but there is nothing we will change as in the vector sense. If we consider matrix as a set of row vectors, if we interchange two rows, we are just interchanging positions of two rows, just positions of two rows. If a vector in null space is perpendicular to all rows, after interchanging rows also, exactly those rows only will be there. So the matrix will be orthogonal to every row in the matrix after interchanging rows also. Similarly, if applying any row operation on the given matrix will not change the null space, because by applying row operations, the rows in the final matrix will be linear combinations of rows in given matrix. What are row operations exactly? We can change two rows. If we interchange two rows, the final rows are the ones in the final row vectors are the ones in initial only. So there is no confusion in that point. If we multiply a row of the given matrix with a non-zero constant, then also the final rows will be linear combinations of initial rows only, because we multiplied one row with a constant. Like if it is v bar, it will become cv bar. Cv bar is anyway by definition linear combination of v bar only. So by applying and third row operation is, if we have two row vectors R1 bar and R2 bar, the third row will be R1 bar minus alpha R2 bar, which is also linear combination of R1 and R2. So by applying row operations, what we are doing exactly is, the rows of the final matrix are just linear combinations of the rows of the initial matrix, and every vector in null space is perpendicular to linear combinations of the rows also. If a vector is there in the matrix A, and now if we are applying row operations on matrix A, that matrix A will be converted to A1. The rows of the A1 are linear combinations of the rows of the A, as we have discussed. As x bar is there in the null space of A, it is perpendicular to every row and every row of the matrix A, and also linear combinations of the rows of the A. The rows in the A1 which is obtained by applying row operations on matrix, which are linear combinations of the rows in A. So the vector x bar in the null space of A will be orthogonal to every row in the matrix A1 also, which is obtained by row operations. Similarly, by applying row operations in the reverse way, if we applied row operations this way, like if we multiplied a row with a non-zero constant, by dividing the row with non-zero constant, by dividing the row with same non-zero constant, we will obtain the matrix we have took initially. So by applying similar row operations, we can get the initial matrix also from final matrix. Like by applying row operations, we can get A to B and B to A also. Like B is the one which is obtained by by applying row operations on A. Similarly, B also, from B also we can get A by applying row operations just in the reverse way. If we have done Ri changes as Cri, we have to do Ri changes as 1 by C into Ra. This way, every vector in null space will be orthogonal to any linear combination of rows in given matrix, which we have already discussed. So every vector in null space of initial matrix will be orthogonal to all rows in final matrix also, because these final rows are linear combinations of the initial rows, and the vector is perpendicular to any linear combinations of the rows in the given matrix. So null space of matrix will not change by applying row operations. We have simple example here to illustrate. Here we have another point also. Null space of here we have another point that so null space of matrix and null space of row reduced echelon form of matrix are same, because we obtained row reduced echelon form of given matrix by applying row operations, and by applying row operations null space will not change, which we have already discussed. Now we have a simple example to illustrate that null space of A is equal to null space of row reduced echelon form of A. Consider matrix 1, 2, 3, 4. Here RREF of this matrix is 1, 0, 0, 1, which we can obtain simply by subtracting first 2 times the first row from the second row. We will get 1, 3, 0, minus 1, and then simply adding 3 times the second row. Like simply we can get RREF of this will be this. You can try yourself finding RREF of this 1, 3, 2, 4 matrix. 1, 3, 2, 4 into x1, x2 equal, let that vector in null space of matrix A is x bar, with let that be x1 and x2, x1, x2. By multiplying we get these equations: x1 plus 3 x2, x1, 1 into x1 plus 3 into x2 equal to 0, and 2 into x1 plus 4 into x2 equal to 0. And from solving that equations, by solving that equations, we will get x1 equal to 0 and x2 equal to 0. And RREF of A is 1, 0, 0, 1. And 1, 0, 0, 1 into x1 and x2, we can get directly x1 equal to 0 and x2 equal to 0. Only 0. So only 0 bar is present in both null space of A and RREF of A. Now we will see another matrix. Find null space of matrix A equal to 4, 5, 2, 3, 2, 1, 4, 3, this matrix. As we have already discussed, null space of A is null space of RREF of A. This RREF of this matrix is this. You can try yourself. We will find null space. This is RREF 1032, which we considered in previous slide. 1032, 01, minus 2, minus 1. Now by getting multiplied and getting these equations, we will get from third row we will not get any information like 0 into x1, 0 into x2, 0 into x3, 0 into x4 is equal to 0. Now we will get these equations. So from this equation, from first equation, we can get x1 equal to 2x3 plus x4. We consider any vector in null space of given matrix as x1, x2, x3, x4. Let it be x1, x2, x2, x4. Now for it should be in for this x bar to be in null space of A, that Ax bar to be equal to 0. So we can get these. We are getting these equations. Now x1, x2, x3, x4. From this first equation, we can get x1 equal to. Sorry, by mistake I have put wrong equation here. 1 into x1 plus 3 into x3 plus 2 into x4 equal to 0. So x1 equal to minus 3x3 minus 2x4, and x2 equal to 2x3 plus x4. This equation is wrong. Like x1 minus 2x3 minus x4 is wrong. By mistake I have put that second equation. The correct equation is x1 plus 3x3 plus 2x4. Here you can see now first row of this 1, 0, 3 to this matrix there na. That matrix into x1, x2, x3, x4. First row of this matrix 1, 0, 3, 2 into x1, x2, x3, x4. x1 plus 3x3 plus 2x4 equal to 0. So x1 equal to minus 3x3 minus 2x4. By putting that by substituting that equations here, we will get every vector in null space of A as linear combination of minus 3, 2, 1, 0 and minus 2, 1, 0, 1. This x3 and x4 has no conditions, so we can put any matrices. So null space of A is null space of RREF of A is equal to, we have found null space of RREF of A as linear combinations of the these matrices, these vectors -3, 2, 1, 2, 0 and -2, 1, 0, 1. So null space of A will be the span of the vector space spanned by -3, 2, 1, 0 and -2, 0, 1. And similarly, we have another space which is column space associated with matrix, defined as linear combinations of column vectors of A. In other words, set of vectors spanned by column vectors of given matrix. In case of null space, if Ax bar equal to 0 bar, so the x bars which are satisfying those equations Ax bar equal to 0 bar will be in null space. But in column space, it is different. Like it is linear combinations of the columns. So let C1, C2, C1, C2, C3, so on, Cn are the columns of the matrix A. M cross n is the given matrix. Number of columns is n. So let the C1, C2, C3, so on, Cn are the columns of A. Now linear combination means B bar equal to some x1 into C1 plus x2 into C2 plus, this way we can write. So B bar is there in column space of A. So it is linear combination of columns of A which are C1, C2, C3, so on, Cn. So B bar equal to some x1, some constant into C1, which is let the constant be x1, some x1 into C1 plus x2 into C2, so on, xn into Cn, which is equivalent to saying that the matrix containing these columns C1, C2, C3, so on, Cn, which is A, because we considered the columns of A are C1, C2, C3, so on, Cn. We can write this statement, this B bar equal to x1, C1 plus x2, C2 plus, this can be written as B bar equal to this x1, C1 plus x2, C2 plus, so on, xn, Cn is there now, that can be written as matrix multiplication, like C1, C2, C3, so on, Cn into x1, x, so on, x into that vector x1, x2, x, so on, xn. Like if we compute this matrix multiplication, you will get x1, C1 plus x2, C2 plus, so on, xn, Cn. So B bar equal to B bar equal to x1, C1 plus x2, C2 plus, so on, xn, Cn is equivalent to saying that B bar equal to this C1, C2, C3, so on, Cn, this matrix is A. So A into x bar, which is there in our next slide. B bar is in column space of A if and only if it can be written as A into some vector x, which is x1 and x2, which are x1, x2, x3, so on, xn, which are coefficients of columns in the linear combination to get B bar. So B bar is in column space of A if and only if it can be written as Ax bar for some vector x bar. So here Ax bar equal to B bar, then only B bar is in column space. But in null space it is different. Ax bar equal to 0 bar, the x bars which are satisfying those Ax bar equal to 0 bar are there in null space. But here there exists some x bar such that Ax bar equal to B bar. B bars are there, not x bars. So B bars will be of order n cross 1, which are different from that null space. In null space, the x bars which are of order n cross 1 will be there, but here m cross 1. Like if the matrix is m cross n, the column space contains matrices of the column space contains vectors which are of order m cross 1. I think there is a little mistake here. This is m cross 1. Like unlike null space, like in null space of a matrix of order m cross n, there are the vectors which are of order n cross 1, but column space contains which are of order m cross 1. Here there is a small mistake, n cross 1, not m cross 1, not n cross 1. Now we will find the column space of A. Column space of A will be span of, why this RREF is here, we will see little bit later. Here we will have that. Like column space of A is just span of the columns of A from definition. But there may be some redundant columns, like for suppose consider this matrix A equal to 4, 2, 3, 5, 1, 4. Here the third and fourth columns will be redundant. Like the third and fourth columns are linear combinations of first two columns. Like how can we say that is? The basis for the column space is pivotal columns in, here we have now, so we have to find basis for the columns of A. We can say that column space of A equal to span of columns of A, but the columns of A may not be basis for columns. Like if the columns of the given matrix A are like A bar, B bar, A plus B bar, that column space of A will be span of A bar comma B bar comma A plus B bar, A bar plus B bar by definition. But the span of A bar comma B bar comma A plus B can be written as span of A comma B also, because every linear combination of A, B and A plus B can be written as linear combination of A, only A and B. Like if it is lambda A bar plus mu B bar plus Z into A bar plus B bar, we can write that as lambda plus Z into A bar plus mu plus Z into B bar. So linear combination of A bar plus B, A bar comma B bar comma A plus B can be written as linear combinations of A bar and B bar itself. So we can remove A plus B. That way, if a column is linearly dependent on the previous column, like if the third column, for example, if third column is linear combination of first column and second column, like C1 plus C2, then that will not add anything to span. So span of columns of A is equal to span of linearly independent columns of A. Like linearly independent, I mean the columns which can be written as linear combinations of others can be removed. Like by removing those columns, we can say that the basis turns out to be columns corresponding to pivotal columns in RREF of A. Here pivotal columns in RREF of A are first and second columns. So first and second columns will turns out to be basis of the column space. For proof, you can refer this link. We have provided a link here. So column space will be span of columns corresponding to pivotal columns. Like what exactly we are saying is, actually column space is span of columns of A, but we are saying it is also span of pivotal columns of A. Means what we can say is non-pivotal columns are redundant. Means non-pivotal columns will not add anything to span, because non-pivotal columns can be written as linear combinations of pivotal columns, which is exactly we have to prove which is provided in the link above. Now pivotal columns in this matrix is in RREF, the pivotal columns are first and second columns. So the corresponding columns which are corresponding to pivotal columns in RREF are first and second columns. So 4, 2, 3, 5, 1, 4. By corresponding, I mean here the first column is pivotal. So first column in A should be in the basis of the column space of A. 4, 2, 3, 5, 1, 4 are first and second columns of the given matrix. So the 4, 2, 3 and 5, 1, 4 will form a basis for the column space. And we have a note here. What we exactly told is, in this proof we have that basis for the column space of A is pivotal columns. So what we can say is non-pivotal, what we have exactly discussed previously is non-pivotal columns can be written as linear combinations of the pivotal columns. So by this way we can find, as you are able to see in the note, we can find linear dependency of the vectors of any given set of vectors. For suppose this question is changed this way, like they given 4, 2, 3, 5, 1, 4, 2, 4, 1, 3, 3, 2. Like that they gave 4 vectors which are 4, 2, 3, 5, 1, 4, 2, 4, 1, 3, 3, 2. Now they asked to check whether these are linearly dependent or linearly independent. What we can exactly do is, you can construct a matrix with the given vectors as the columns, and you can find RREF of that matrix. And pivotal columns will form a basis for the, as we have already discussed, pivotal columns will form a basis for the column space of A. So non-pivotal columns can be written as linear combinations of pivotal columns. So they given 4 vectors, but there are only 2 vectors in the basis. Like if they given 4, 2, 3, 5, 1, 4, 2, 4, 1, 3, 3, 2, they gave 4 vectors, but there are only 4, 2, 3 and 5, 1, 4. That first row and second row are only there in the basis, which means 2, 4, 1 and 2, 4, 1 vector and 3, 3, 2 vector can be written as linear combinations of these first 2 rows. Linear combinations of these first 2 rows means these vectors 4, 2, 3, 5, 1, 4 are 5, 1, 4, 2, 4, 1, 3, 3, 2. These 4 vectors are linearly dependent, because at least one vector can be written as linear combinations of others. So these vectors are linearly independent, not linearly independent, they are linearly dependent. By this way we can find linearly. So this is another use of RREF. We have that very weird definition of RREF. We don't know why that weird definitions, but we have one application here. We have one application here, that is, if they given a finite set of vectors, we can find whether they are linearly independent or dependent by constructing a matrix which contains the columns as the given, which contains the columns which whose columns are the given vectors. Like as previously I told, we will consider a matrix whose columns are the given vectors, and we will find RREF. By this way, we can find linear dependency or independence of the given vector, given finite set of vectors. This is one application of RREF. And here row space and left null space, these are like column space and null space only. Row space is a set of vectors spanned by, like, column space is set of vectors spanned by column vectors. Here row vectors, just row space, everything is replaced by row. Column space is set of vectors spanned by column vectors. So row space is set of vectors spanned by row vectors, or set of all vectors which are linear combinations of row vectors of matrix by definition of span. This can be easily calculated by finding column space of A transpose, because in A transpose, column space of A transpose means they are linear combinations of columns of A transpose. Columns of A transpose means which are directly rows of A. So for finding row space of given matrix, you can find the column space of the transpose, because these rows are converted into columns in the transpose, and we have already seen how to find column space. And left null space is we have already seen null space na Ax bar equal to 0 bar. That way they are null space. Left null space is that x bar is up multiplied from left side, like just x bar into A equal to 0. X bar into A equal to 0 means A transpose into x bar transpose equal to 0. Like by AB whole transpose can be written as B transpose into A transpose. So x bar A whole transpose equal to 0. So A transpose into x bar transpose is equal to 0. So this way we can say that, let us assume A transpose is given matrix. Now A given matrix into a vector is equal to 0, which means that x bar transpose is present in the null space of A transpose. So left null space is set of vectors which are transpose of the vectors in null space of A transpose. Like A transpose into x bar transpose is equal to 0. So this x bar transpose vector is there in null space of A transpose by definition, because some matrix A into x bar, some matrix into x bar equal to 0 means x bar is there in null space of A. Here that matrix is A transpose itself, and the vector is x bar transpose. So that x bar whole transpose is a vector which when multiplied with A giving 0 vector. So this x bar transpose will be present in null space of A transpose. As x bar transpose is present in null space of A transpose, we can find first null space of A transpose. So we will get all the vectors x bar transpose. This x bar transpose is there na, that all such vectors we will get, which when multiplied by A transpose is equal to 0. Now x bar transpose are the vectors which when multiplied by A transpose are 0. Now we will transpose this x bar transpose again. Like there is no confusion here, because x bar transpose whole transpose is equal to x bar, because transposing 2 times means we are mirroring 2 times. So we will get again the same matrix. So left null space of A is set of vectors which are transpose of vectors in null space of A transpose. Today session is completed. Do you have any doubts about this null space, left null space, row space, column space? You can feel free to ask in chat. Having any doubts? Like if you have any doubts, feel free to ask in chat box. Or we will close the session in 10 minutes, in 5 minutes. If no one has doubt, we can end the session.
Like 1 minute. So some people wanted the attendance again. So can you share it? Athray, can you share the attendance once? or Girish, can one of you share the attendance form again?
Atriya, are you sharing or should I? Okay.
Okay, if there are no doubts, we can close session, I think.